Hello everyone and welcome to MATLAB and Simulink tutorials. In this tutorial, we explain how to simulate dynamical systems by using MATLAB S-Functions and Simulink. A MATLAB S-function is a code description of a Simulink block written in MATLAB, C, C++, or Fortran. S-functions use a special syntax called S-Function API that enables us to easily define what a Simulink block should do and to interact with the Simulink blocks by using code scripts. This enables us to increase the flexibility and power of the modeling process in Simulink. For example, by using S-functions, we can define all the steps that are performed during a typical Simulink simulation. For example, we can set the initial conditions, define how derivatives are computed, and directly define states and outputs as well as the dynamics of the system, and everything is done inside of a script. This can significantly speed up the modeling process and lead to parametric, generic, clean and disciplined implementation of the Simulink simulation. Also, if a model is complex with a large number of state space variables, it is often impractical to model every component as a basic Simulink block. Instead, we can write a model as a script and embed the model inside of a Simulink block. For that purpose, we use S-functions. There are level 1 and level 2 MATLAB S-functions. In this tutorial, we explain how to use level 1 MATLAB S-functions. According to the information provided on the MATLAB website, it is suggested to use level 2 S-functions. Level 2 S-functions are more capable. However, a large number of simulations are written by using level 1 S-functions, and our experience shows that level 1 S-functions are better documented with a large number of examples that can be found online. In the future tutorial, we will explain level 2 MATLAB S-functions. And our suggestion is to first learn how to write level 1 S-functions, and then you can easily learn how to write level 2 MATLAB S-functions. Here's the test case that we will consider in this video tutorial and that we will simulate in Simulink. Our problem is to simulate a dynamical system in the state space form for given initial conditions and for given system parameters k1 and k2. Here's the state equation. This state space model has two state variables, x1 and x2. The first equation tells us that x1 dot is equal to x2, and the second equation tells us that x2 dot is equal to minus k1 sine x1 plus k2 multiplying u. Over here, u is the control input. k1 and k2 are the model parameters. Some of you might be familiar with this model. For precise values of k1 that depend on the physical parameters of the model, this is actually a pendulum model. And this model is very popular in control engineering world. Okay, let's start with implementation. The first step is to write our S-function. Luckily, we don't need to write the S-function from scratch. Instead, we can use a template. Let's open the template. To open the template, in the command window, type open, then under single quotations, type S-fun, S-F-U-N, and T-M-P-L. So again, you need to type open S-fun, T-M-P-L. Note over here that the last letter is not 1, it is L, and press enter. And voila! Here is the S-function template file. And we are going to edit this file. Note over here that every MATLAB installation comes with this file. If not, I'm going to also provide a link to this template file in the description below this video. The next step is to modify the name of the function inside of this template and to save this file and to give it some other name. So let's call our function over here simply as function1s. Okay, next, don't save it immediately. Make sure that you click over here and click on Save As. Now, why you should do this? Because you don't want to destroy this nice template which is saved in this MATLAB folder. Instead, you need to save it somewhere else. So navigate to the folder where you want to save this file. For example, you can create a folder. In my case, it's under codes. And over here, I have a special folder that I'm using for testing. And let me just find it over here. So the folder is located, let me see. Here it is. Okay, and now I'm going to give the name to this file. However, the name of the file should precisely match the name of this function over here. That is, if the name of the function is function1s, the file should be called like that. So let's type over here function1s and let's save. Now let's make sure that the names are matching. Function1s, function1s. Perfect. If you scroll all the way down and if you look into this file, you can see that this file is well documented. That is, there are a large number of comments in this file, and my suggestion is to go over these comments and to try to better understand how this file is written. Here, for brevity and for clarity, we're just going to mention the main portions and main segments of this file, and we will explain how to implement our dynamical system inside of this file. Okay, so let's start from this line over here. The name of the function is obviously function1s. Over here, t is time, x is the state, u is the external input, and we have this flag over here. So how does this function works and how does Simulink use this function? During simulation of a model, the Simulink engine repeatedly invokes this function over here using the flag argument to indicate the task or tasks that need to be performed for a particular simulation. This S function performs the task and returns the result in the output vector. And over here you can see also the outputs. As you will see later on, this function will be embedded inside of a Simulink block. And this input over here is actually the input to the Simulink block. T is the simulation time, and this flag is the internal flag that's used by the simulation inside of the Simulink world. Okay, over here we are going to modify these input parameters and we are going to add initial conditions. Let's add x01 for x1 and let's add x02. And let's make sure that we save this file. Okay, let's now scroll down and you can read these comments over here. Basically, this file switches and investigates the value of flag. And over here you can see several values of flag. When flag is 0, this means initialization, return system size insist, initial state in x0, state ordering strings in str, and sample times in ts. Then you can see when flag is 1, return continuous state derivatives in system. This is very important for us, and this is very important for us. For every flag, there is a function or a handle that handles a particular situation. First of all, we will need to initialize. So let's do that. So let's go down, and let's find where the code starts. The code starts over here, and we can see that we are investigating the value of flag. Internally, inside of the Simulink simulation, flag will first be equal to 0. And we don't need to control the flag. Flag is automatically switched to 0, 1, 2, 3, etc. However, over here, we need to do several modifications. Case 0 means that we are initializing. So over here, we need to pass to this function the values of x01 and x02. So let's copy them over here. Let's go over here to line 108, and over here in parentheses, let's type x01 and x02. Now we are passing to this function MDL initialize sizes x01 and x02. x01 and x02 are provided by the user, and I will explain later on how to set these initial conditions. Okay, so let's now find where do we use this function, or where this function is defined. So let's copy this, let's search function, and let's see it over here. So here it is. Now, let's now over here, again, type x01, x02, since we need to change the definition. Let's make sure that this definition matches this definition. Let's just copy over here. And let's make sure that everything is okay. Perfect. So let's see what's happening over here inside of this definition. The definition starts from the line 156. First of all, we are not going to change this value over here. This is the internal value inside of the Simulink simulation. However, over here we are going to change the number of continuous states. That is, size dot num cont states stands for number of continuous states. Obviously, if you look at our model has two states, x1 and x2. Consequently, over here, we're going to set 2. Next, this variable over here is the number of discrete states. Since our system is in continuous time domain, we don't have discrete time states. Okay, good. Next, we need to specify the number of outputs. We will have 2 outputs. The outputs will be x1 and x2. Next, we need to specify the number of inputs. We have a single input, and that's our u. So let's see the model again. This is our input. Do we have a direct feed-through term? Okay, let's analyze. By looking at this model, we don't see a direct feed-through term over here. So going back over here, let's specify 0. Next, let's keep this variable num sample times, or the number of sample times, to be equal to 1. In this way, we are telling to Simulink that we want to use the standard Simulink sampling times. Of course, you can also implement a multi-rate system over here. Let's not change this line, and over here we need to make a very important modification. We need to specify the initial condition for our simulation. Okay, going back to this definition, we just need to copy this part, x01 and x02, and we need to paste it over here and save it. Now we are specifying the initial conditions, and that's it. The rest of this function shouldn't be changed. Good. This was the case 0. In case 0, we initialize our system. Okay, let's continue. Now go back to line 113, and let's analyze what's written over here. Over here, we need to compute the derivatives. That is, we need to specify the right-hand side of our equation. So let's do that. This function is defined later on in the code. Consequently, let's copy the name of the function, and let's search for the matches. Here it is. The definition starts on the line 207. This function will return the derivatives for the continuous states. The inputs are time, state, and input. And over here, let's type. First of all, let's type this. dx1 that is the first derivative of x1, is equal to, look what I'm writing now, x of 2, and semicolon. So what's happening over here? X is a two-dimensional row vector. And over here, I'm simply saying that x1 dot is equal to x2. That is, I'm specifying the first equation. Good. Let's specify the second equation. So if we go back here, we need to write dx2 is equal to, okay, we need k1 multiplying, however, we need with the minus sign of x of 1, okay? And then we have plus k2 multiplying u and semicolon. However, here we didn't define k1 and k2. Let's set k1 to be equal to 1 and k2 to be equal to 1 also. Good. In a more generic simulation, you can also pass k1 and k2 as the parameters of the S-function, similarly to the initial states. However, here, for simplicity, we are not going to do that. Good. Now, over here, we simply have to say that this cis array, or a row vector, is actually equal to dx1, dx2. And that's it. That is, cis is a row vector that returns the first derivatives of x1 and x2. That is, cis defines the value of the right-hand side of this equation for fixed values of x1 and x2. That's it, simple as that. Let's make sure that everything is defined over here. k1, k2, dx1, dx2, cis, and that's it. Here we have x1 dot is x2, x2 dot is minus k1 sine x1 plus k2 multiplying u. Perfect. Okay, now we have completed case 0 where we initialize and case 1 where we compute the right-hand side or the derivatives of our state space model. Case 2 applies to discrete time system, and case 2 is an equivalent of case 1 for discrete time systems. That is, if you have a discrete time system, instead of using case 1, you're going to use case 2. Let's continue. Here is a very important part. Over here, we need to specify the outputs of the system. That is, we need to modify the function MDL outputs. So let's find the definition of this function. Press Ctrl F and search for MDL outputs. And let's go over here. And here's the function. The function is super simple. We're simply going to return as the output the state x. And that's it. Simple as that. Let's close this and let's continue further. And let's see, do we have to modify something like this? We don't need to modify this part over here. We don't need to modify terminate, and that's it. Simple as that. This was our function 1s. Perfect. Let's save this and let's continue. Next, let's make sure that this folder is in your MATLAB workspace. That is, first of all, modify over here the path such that this folder where this file is saved is the currently active folder. You can also try to use some commands such as this command, which is a command prompt, and you can see that you can actually see these two functions. However, let's make sure that everything is done properly. So click on Home, then click on Set a Path, then click over here Add with Subfolders, and locate the folder. So the folder is C codes. Let me find it. Here is the code. Here's the file. Let me just find it over here and select this folder. And don't click on Save, since I don't like to save it. Simply press over here, and do you wish to save the current path for use in future MATLAB session? I usually say no over here. However, now this folder is inside of the MATLAB path, and our Simulink model will be able to see this folder. Okay, the next step is to start Simulink. Actually, here I made an error. You should type Simulink, S-I-M-U link, and press enter, and Simulink should start. Next, let's click on blank model over here. And wait for some time, and let's start with implementation. First of all, we need to create an S-function block. To do that, double-click here and search for S-function. And click over here. Let's expand this block, double-click on the block, and over here we need to specify the name of the function. For that purpose, you need to remember the name of the function. That is the name of our S function. In our case, it is function 1s. Now, here you can click on edit, and if you have properly specified the name, Simulink will be able to automatically find the file that defines the function. And here it is. Perfect. Let's go back to our definition over here and to our Simulink model. Okay, so over here we need to specify the S-function parameters. The S-function parameters are actually the initial conditions inside of our function. Namely, if you go back to this function and if you analyze the parameters, you will see x01 and x02. Then inside over here you need to specify the numerical values of these parameters. Let's start, for example, with 1, then comma 0. In this way, you're specifying the additional parameters. Over here, if you have extra parameters, then you will need to add as many commas and as many numbers as the number of the parameters over here. Let's click on apply and let's click OK. Next, let's go back to our Simulink model. First of all, we need to add the input. Let's start with a simple step signal. Over here, double click and let's search for constant. Here it is. This is our U. Double click over here and let's specify the value to be equal to 2 and apply and OK. Next, connect the output of the constant block to the input of the function 1s. Good. However, our function actually has two outputs or a single output. Let's see that. This is very important. Now, let's go back to the function and let's see what do we have over here. If we now scroll all the way down and if we go over here to definition of this function, MDL, initialize sizes, you will see that the number of outputs is equal to 2. Consequently, we will have two outputs coming out of our function s. However, we would like to plot both outputs independently. So let's learn how to do that. To do that, click over here and search for dmux or dmux block. Now connect this part. And what's happening over here? This output over here has two variables, x1 and x2 as functions of time. This port of dmux or demux will extract x1 and the second one will extract x2. Consequently, let's search for scope over here such that we can plot x1 and let's double click again and search for scope such that we can plot x2. Good. Next, we can add an additional scope to plot both functions on the same graph. For that purpose, we simply need to connect this block over here, and that's it. Let's make sure that the initial conditions are properly set. Double click here. They are. Let's adjust the simulation time, for example, to be 15. And then let's finally run the simulation. And let's hope that everything will be fine. It is. We don't see any errors or any warnings. So let's see the outcome of our simulation. Double click over here and you will see the variables. You will see the first one and you will see the second one as a function of time. And over here you will see the first one and you will see the second one. Now let's analyze these results and let's see if they are realistic. Double click over here and let's see what's happening. To see what are the variables, click on View and click on Legend to see the legends. The yellow one is x1 and the blue one is x2. Now, it seems that x1 is exponentially growing as well as the x2. Well, is this realistic? This is a good question. It looks like over here that we have specified a large value of this force, and this might lead to significant rotations of our pendulum. So let's decrease the value of the force over here. Double click here and let's specify the force to be equal to 0.1 and click on Apply and click OK. And let's again run and let's see what will happen. Then again, let's click over here and here it is. Now the things look much more realistic. We can see that x1 oscillates and x2 also oscillate. The next question is this dynamical system properly implemented? Well, let's analyze. If we go back to our simulation, we can see how x1 and x2 are related. Or if we analytically analyze this, we can see the relationship. Okay, next, going back to the Simulink model, let's try to double check that everything is as it should be. To do that, let's double click over here and let's specify the value of force to be equal to 0. Now, if we double click over here, let's make sure that this initial condition is 1, that is, the initial position or angle of rotation is 1, and the velocity is 0. And let's now run again. And let's see the results over here. And let me do it again. Here they are. Let's analyze. Now, x1 dot is x2 and x2 dot is minus k1 sine x1. What is also important to observe over here is that x1 dot and x2 are related. That is, the x2 is the first derivative of x1, or better to say, x1 dot is the velocity and x1 is the angle. Or better to say, x1 dot is the angular velocity and x1 is angle. When the angular velocity is equal to 0, the angle should reach the maximum value. And we can see it over here. That is, when blue line crosses 0, the yellow line has the minimum or maximum. And we can see it over here. Here the maximum is achieved. When the blue line crosses 0, the yellow line has maximum, then again over here minimum is achieved, etc. This means that this is a proper implementation of the pendulum model. And that's all for today, and thanks for watching.